All right, so just some review. They say let negative 7, 3 be a point on the terminal side of the angle. And they want us to find all 6 trig functions. So we're going to draw a triangle with this one. We're going to plot negative 7, 3, and we're going to draw a triangle. So our triangle is always drawn with the x-axis to the origin with theta on the x-axis, okay? So there's our right triangle. And negative 7 for the x value and 3 for the y value, because that's the point they gave us, the x and the y. We can use Pythagorean theorem to find that third side. So negative 7 squared plus 3 squared equals c squared. So c squared equals, let's see, 49 plus 9. So c has to equal the square root of 58. Square root 58, like that. And then from there we can write all 6 trig functions. So sine of theta, cosine of theta, and tangent of theta, and then cosecant of theta, secant of theta, cotangent of theta. Okay, so this is our game plan. This is our method when we don't really know what theta is. We will never ever find out in this problem how many degrees or radians theta is, but we don't need to know it to be able to have 3 side lengths and be able to write all of these fractions, these ratios for our trig functions. Okay, so if we don't ever know what theta is, this is our plan. Go ahead and fill in those ratios and then check your answers in a moment. All right, check those answers in a moment. That seems, writing these fractions is the easy part, as I'm noticing. It's going to be drawing that triangle or correctly calculating that hypotenuse that trips people up. So watch out for that. All right, this example gets a little more involved because we have to actually narrow down which quadrant this thing is located in. So to do that, we use our little all students take calculus mnemonic device here. So remember, these stand for the functions that are positive and which functions are positive in that quadrant. So sine and its reciprocal here, tangent and its reciprocal there, cosine and its reciprocal here, and then of course everything is positive in the first quadrant. So when they tell us that sine of theta, right here, sine of theta is less than 0, well, they're telling us that sine is negative. Sine is negative, so I have to cross out the places where sine is positive. I know that sine is positive where everything is positive and right here at S. So sine is positive there. It is not going to be negative. This would be impossible in these 2 quadrants because sine is positive there. And then for the remaining 2, I have to go use this ratio here. So cotangent, which follows along with tangent, right? It's the reciprocal of tangent, it is a positive fraction. So of the 2 remaining quadrants, where is tangent and cotangent positive? Well, right here. Okay, if it was in the 4th quadrant, cotangent would not be allowed to be positive. So that C stands for cosine, not cotangent. So now I know I need to draw my triangle in the 3rd quadrant. And so here's my triangle, the terminal side right there, forming a triangle with the x-axis and theta on the x-axis. Okay, and then I need to remember, using SOHCAHTOA, what side over what side cotangent is. So SOHCAHTOA reminds me that tangent is opposite over adjacent. So therefore cotangent is adjacent over opposite. They have given me the adjacent side of 3 and the opposite side of 4. And this picture looks really complete, except you have to remember that anything left is negative and anything down is negative. So that is actually a -3 and a -4. And it's a 3, 4, 5 triangle. But this is the most missed part on a problem like this. People forget that it is left and down. Those negatives don't pop up in this ratio because negative divided by a negative is positive, but they are there because it is left and down. Okay. And they're going to pop up in your other trig ratios. So let's go ahead and write those out. All right, and there are our remaining trig functions, the other 5 that we didn't know, along with the one that we knew. Okay, So just watch out for tangent and cotangent. They get tricky in the third quadrant because that negative divided by a negative cancels out and makes a positive ratio. Okay, so one of the things I'm going to be asking you to do is to find the reference angle. And we've already been talking about how to find the reference angle in the problems that we did earlier in these slides, in these notes. We've probably talked about it more like this, where I told you to draw a triangle, and no matter where your triangle was drawn, whichever quadrant, maybe let's say hypothetically it's in quadrant 4, with which axis did I ask you to draw the triangle? I always told you to draw the triangle with the x-axis. And where did I tell you to put the theta? At the origin on the x-axis, right there. And I've been telling you that because that is our reference angle spot. This is the reference angle spot. So an easy definition of a reference angle. You have two options. You can either memorize all 4 of these formulas, which, woohoo, if you love memorizing formulas, you have at it, or you can remember this quick definition of a reference angle. A reference angle is the angle between the closest x-axis and the terminal side. The reference angle is the angle between the closest x-axis and the terminal side. It doesn't matter how the terminal side got there. It doesn't matter if it went positive or negative. It doesn't matter if it took extra laps. It doesn't matter if it's a unit circle angle or not. It doesn't matter if it passed the x-axis or if it didn't quite reach that x-axis. The reference angle is the closest x-axis to the terminal side. It is always positive and it is always acute. Always positive and always acute. Okay. So let's find some reference angle. On these 6 examples here, I'll show you 60. Sometimes your reference angle is the exact angle that you're given for the terminal side. So 60 degrees is like right here, right? We rotated 60 degrees to get there. And then where is the closest x-axis? Well, it's this positive x-axis right here. So how many degrees are in between this positive x-axis and the terminal side? Don't overthink it. It's 60 degrees. So sometimes it's the exact angle you're given, but sometimes it's not. Let's look at 11 pi over 6. So if we plot this angle, 11 pi over 6 is, well, if you're not so good yet on the radians, remember I told you to mark the half circle spot by the denominator. So the half circle is pi, or we can call that 6 pi over 6. So does 11 pi over 6 make it to 6 pi over 6? Yes. In fact, it almost makes it all the way around. So 11 pi over 6 is right here. This is 11 pi over 6. It rotated that much to get there. So how much is between the terminal side and the closest x-axis? How much is right there? How many pi over 6s would it take to get all the way to 12? 1. It would take 1 more pi over 6 to get to 12 pi over 6, that full circle spot. So pi over 6. So our reference angle is always positive, and because we're going to the closest x-axis, it will always be less than 90 degrees. You should give me the reference angle in the unit you were given, okay? So don't convert 11 pi over 6 to degrees and then tell me the reference angle is 30 degrees. That will not get you credit. It is not 30 degrees. It is pi over 6, okay? Stick to the unit you're given. Why don't you give these other 4 a try, and I'll throw some hints up there along the way. There are some hints for you about like where on the unit circle you'd be looking, or not on the unit circle, just where in the rotation that terminal side lands. You know, and then on these radian measures, I marked the half circle spot. And then my tip for 17 pi over 3, if you're stuck on that, 17 pi over 3 obviously takes extra laps, right? What's a full circle in radians? 2 pi. Okay, what if you're counting by pi over 3? How many pi over 3 is a full circle? Yeah, double that 3. 6 pi over 3 is a full circle. So are there any full circles in 17? If 6 pi over 3 is a full circle? Yes, there are full circles. Can I just take them out, though? If I take out a full circle, is it still going to land in the same spot? Yeah, that's how we find coterminal angles. We take out a full circle, or we add in a full circle. And so these will still terminate. They'll still have the same ending spot, but I can take out a full circle. So if I take out a full circle, that gets me down to 11 pi over 3. Still lands in the same spot as 17 pi over 3 did. And there's another full circle in there, isn't there? So let's take out another full circle, because this is just too much to manage. So 11 pi minus 6 is, we get down to 5 pi over 3. That's better. That's something that, as you do enough of the unit circle, you remember that lands right here. 5 pi over 3. 17 pi over 3 would have landed there as well. And you could have counted your way around. Here, I'll show you how that would have worked. 0, 3 pi over 3, 6 pi over 3, 9 pi over 3, 12 pi over 3, 15 pi over 3, 2 more pi over 3 gets you to 17 pi over 3. But I've never met someone who was excited about counting their way around by pi over 3. Okay. All right. Why don't you go ahead and finish these up, and I'll put my answers up there. All right. So as you finish up, check those answers up there. On this -203 one, I rotated in the negative direction, and you know, half of a circle of rotation is 180 degrees. So you got to subtract 203 minus 180 to get this difference here, this 23 degrees. Okay, 265, same idea. That's 85 degrees past the half circle, past 180. Okay, 85 degrees there. And then over here, if you 7 pi over 12 doesn't make it to 12 over 12, but 5 more would get it there, so 5 pi over 12. 5 more to get to 12 pi over 12. Okay? All right. Let's do some trig with your unit circle. So you've got your unit circle in front of you. It's filled out properly now, and I have told you or reminded you about the usefulness of this unit circle, that if you want to know sine, cosine, or tangent of any angle on that circle, you're staring at it. It's in the coordinate. So sine, remember the stuff I wrote out to the side. Sine of theta wants the y value, you know, and it's technically the y value over the hypotenuse, but the hypotenuse is always 1 on the unit circle, so we don't worry about that. Cosine of any unit circle angle is the x. And then what was tangent? Tangent was y over x. Okay, y over the x. And then our reciprocal functions would just take that answer and flip it. The reciprocal of y, the reciprocal of x, or cotangent would want x over y. So a quick way to remember this, S and C, I always think x, it goes, you know, coordinates, they always go x comma y in alphabetical order, and so does C and S. C comes before S alphabetically. So cosine is the x, sine is the y. So here's how this works. Sine of 30 degrees, I know because it says sine that I'm looking for the y part of the coordinate. And so I am glancing at my unit circle at 30 degrees, which is right here. And I'm snagging the y part of that coordinate. The y part of that coordinate is the answer, 1/2. Okay, look up here. You don't have to do this part. I just do that so that when we're working together, you can see where I want you to be looking on your unit circle. All you have to do is write the answer. You don't have to plot the angle. I'm just doing that for you. Okay? All right, let's try another one. Cosine of pi over 3. Cosine wants the x part. So I'm looking at my unit circle at pi over 3, which is right here. And I'm giving the answer which is the x part of that coordinate, which is 1/2. And that's all you have to do. So why don't you try the other two on this page, see if you can get those on your own. All right, so there are some hints there for you. Those are the two places on the unit circle that I want you to be looking at. For negative 45 degrees, notice you rotate in the negative direction. Is that spot called negative 45 degrees on your unit circle? No, what's your unit circle have that labeled as? 315. But they are the same place. Negative 45 is coterminal with 315. So it's the same place on the unit circle. You're doing the same thing. Cosine wants the x. So the x part of that spot is root 2 over 2. Root 2 over 2. And then 7 pi over 6. Sine wants the y part. So at that spot at 7 pi over 6, the y part is negative 1/2. 7 pi over 6. Hey, try these next 4 examples. We're just going to do a lot of these. We're going to start burning through them. After you do about 15 or 20 of them, you're going to feel like, okay, this is actually pretty easy. The hardest part is going to be filling out my unit circle. So give these 4 a try. I'll put a hint up there in a moment. So if you're stumped on any of them, take a look at the hint there. I showed you where you should be looking on your unit circle for each of these. A lot of people miss the negatives on sine of negative 120. They just go straight to the unit circle to the 120 spot. They just use that coordinate. It's not that coordinate. You got to rotate in the negative direction. As you finish up all 4 of these, check your answer up here. Okay, hey, there's a typo on this page. So sorry, I meant to delete these 4. All right, so just do those 4. And notice all these land on like 90 degree family. But the rule still applies. Cosine wants the x, sine wants the y, tangent wants the y over the x. If you need a hint, I've drawn up on the board what angle you should be looking at on your unit circle. Negative 450 is tough. You can take out a full circle by adding 360 if you want to, or you can count your way around until you get to negative 440. So I just went ahead and counted my way around. Negative 90, negative 180, negative 270, negative 360, negative 450, right there. Check your final answers up there. Is that what you guys got for these 4? So this is getting pretty simple, right? For sine and cosine, it's not too bad. Let's go to the next one here. So we got tangent. We got tangent. Remember, cosine wants the x, sine wants the y, tangent wants what? Yeah, y over x. So at the top, when I took pre-cal, one of the things I wrote at the top of my quizzes and tests was I did this. C, comma, S for cosine on the x, sine wants the y, and then I wrote tangent is y over x. And remember, this only works if theta is on the unit circle. If we're talking about a theta that you don't know, like you don't know what the angle is, you can't do this trick where cosine is the x, sine is the y. This only works for angles that are known to be on the unit circle. Okay. So let's check this out. Tangent of 60 degrees. So 60 degrees is right here, and that coordinate is 1/2 root 3 over 2. And so tangent doesn't want the x or the y, it wants the y over the x. So I'm going to set up a fraction here. Root 3 over 2 divided by 1/2. Do you remember how to divide fractions? To multiply fractions, you keep, change, flip. Keep, change, flip. Remember that? Keep the first fraction. change to multiply, and then flip the second fraction. And what's going to happen with the 2's? Yeah, the 2's are going to cancel out. So to be honest with you, if you do keep, change, flip every time, the 2's are always going to cancel. If you're dividing two fractions and the denominators are the same, they're always going to cancel. So most people don't even show this keep, change, flip work. They know the denominators are going to flip or change. They know that the denominators are going to cancel right away. But if you don't notice that, you're welcome to do keep, change, flip. You'll still get root 3 as your final answer. Okay, root 3 over 1, which is root 3. Okay, so give that a try for all three of these others. All right, tangent of 5 pi over 6. So at that spot, the y value is 1/2. The x value is negative root 3 over 2. And so, yeah, the 2's are going to cancel. You're welcome to take that shortcut. As soon as you stack the fractions, you know that these two fractions share a denominator. It's going to cancel. Okay, so you end up with 1 over negative root 2, or root 3. 1 over negative root 3, which is a perfectly fine answer, except are you going to see it like that on the multiple choice section? No. In most multiple choice tests, they're going to rationalize that denominator, so they're going to call it root 3 over 3. So I'll box both of them, because really either one of them is fine, but you'll see it in rationalized form on the test. So 225 is an interesting case. 225, that's the y value, negative root 2 over 2, divided by the x value, which is the exact same thing. So what happens when you divide something by itself? What's the answer? 1. So tangent of 225 is 1, positive 1 even, because negative divided by a negative is positive. And then tangent of pi, well, the coordinate there is negative 1, 0. So the y over the x there is 0 divided by negative 1, which is 0. Hey, real quick, what would cotangent of pi be? Cotangent. Cotangent would want the x over the y, wouldn't it? And if I was forced to write the x over the y, I'd have to write negative 1 over 0. Can I have over 0? No, so I'd write undefined. Right, divided by 0 is undefined. We'll see an example like that on the next one. Okay, here we go. I think we already did a few of these. Yeah, for the sake of time, let's focus on these reciprocal functions: cotangent, secant, cosecant, and cotangent. Focus on those 4. All right, so these reciprocal functions, let's jot down some locations for these angles first of all. 11 pi over 6 right there in the 4th quadrant. Negative 5 pi over 4 in the 2nd quadrant. 510. If I take out 360, that's 150, so that's in the 2nd quadrant. And then cotangent, pi over 2. Well, pi over 2 is right here, pi over 2. Cotangent wants it is the reciprocal of tangent, so it wants the x over the y. Secant is the reciprocal of what? Secant is the reciprocal of cosine. Cosine is the x, so secant wants the reciprocal of x. Okay. Secant wants the reciprocal of the x, because it's the reciprocal function. Cotangent wants the x over the y, the reciprocal of tangent. And cosecant, whose reciprocal is cosecant? Sine, which is the y. So cosecant wants the reciprocal of the y. Okay. So you're still drawn to the x and the y, and still writing fractions for tangent and cotangent, but you're just doing reciprocals. So for for cotangent at this location, that would be root 3 over 2 divided by negative 1/2. The 2's cancel out, and you're left with negative root 3. Right, the 2's cancel. Over here on secant, well, that spot is the reciprocal of the x. The x is negative root 2 over 2. So to reciprocate that or flip it, well, directly it would be negative 2 over root 2. And then to rationalize it would be negative 2 root 2 over 2, which is negative root 2. Either of these would be fine. But you'd probably see the second one in the multiple choice section. And then 510, like I said, 510, if you subtract 360, then 510 is equal to 150. So that's how I located it right there. And they want the reciprocal of the y. The y value at that spot is 1/2. So the reciprocal of 1/2 is 2. 2 over 1. And then at pi over 2, cotangent wants the x over the y. So the coordinate here is 0, 1. Look, if you did y over x at pi over 2, you would get undefined. And do you know how to flip the word undefined? No, that doesn't really make any sense to flip the word undefined. So for cotangent, I would just go ahead and memorize that cotangent is x over the y, as opposed to remembering it as just flip tangent's answer. Okay? Because sometimes tangent's answer is undefined, and that can get confusing if you're trying to flip undefined. So cotangent is the x over the y, which in this case is 0 over 1, which is 0.